Okay, so to draw and label the free body diagram, first of all, we've got the weight that acts straight down, the normal force, which acts perpendicular from the surface, and if the block is sliding down the incline and friction is present, force of friction opposes motion. So that's all you need to do to draw and label the free body diagram. For B, the force that acts down the incline. The force that acts down the incline acts parallel to the surface. And remember, the parallel force is when we do the weight sine of theta. So that mass times gravity, sine theta, 4 times 9.8. Sine of 30 degrees gives us the component of the weight that acts down the incline. And what I got was 19.6. So 19.6 newtons. And then, for part C, what would be the acceleration if there's no friction? Well, if there's no friction, if you're asked to find the acceleration, because F equals ma. Remember, the net force equals mass times acceleration. So it's also commonly written as acceleration equals net force over mass. Same thing, just rearranged for acceleration. Well, what's your net force down the incline? If there's no friction, it's just 19.6 newtons. And how would we know that? If you're looking for the net force, think about the direction the object is accelerating, because that's a good place to start. The direction of the net force has to be the same direction as the acceleration. And if we have no friction, our net force is just that force that acts down the incline, 19.6 newtons, divided by the mass of 4 kilograms. And so without friction, our acceleration, I get about 4.9. And acceleration is meters per second squared. And then part D, let's say we do have friction. How do you think friction is going to impact the acceleration of the block down the incline? Is it going to make the acceleration more or less if we have friction? Less. We will have less acceleration because friction slows down the motion. So if it's accelerating down the incline, then we can subtract the friction because it's going to be less. So the acceleration, which is net force over the mass, we start off with the force that acts down the incline, since that's the direction of the acceleration. The force down the incline was 19.6 newtons. We're going to subtract friction. Remember, the force of friction is the fun equation. That is the coefficient times normal force. The coefficient given to the problem is 0.3. The normal force while we're on an incline isn't just the weight, it's the weight cosine theta. So the weight times cosine theta, all divided by the mass, 4 kilograms. So again, the net force for the block down the incline was the force that acts down the incline, parallel, minus friction, which is going to slow down that acceleration down the incline because it opposes motion, all divided by the mass. Make sure your calculator is in degrees. And then we solve for the acceleration. And to 2 significant digits, it's about 2.4 meters per second squared. Okay. So a lot of different things happen there. That was our first inclined plane problem. But you find the weight the same way. The main difference is your parallel and normal force. Once you find those, you're still using like F equals ma the same way we always have. It's just adding one more thing. So our parallel force is the force that acts down the incline. Acceleration is the force down the incline divided by the mass because the block is accelerating down the incline. In part D, we did the same thing, but we had to subtract friction. We subtracted friction because it's going to slow the block down, which means it has less acceleration. All right. And so for the remaining time, I've got one more inclined plane problem that's similar to this one. I want you to try this one on your own, and if you get stuck, you can refer to this problem to help you out. Okay? So here's the next inclined plane problem. So if you want to draw this one and actually try answering the questions, the first thing we're going to do tomorrow is go over the correct answers to this one.